Hi and welcome to John's Maths book. In this video, we're going to be looking at a real-life problem involving differential equations and finding a solution. If you like the video, please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. Let's look at how we can apply the technique of solving differential equations by the separation of variables to a real problem. Let's suppose we have a full can of lemonade and a very thirsty person comes along, opens the can and inserts a straw. The depth of lemonade in the can is given by variable h in centimeters and the radius of the can is 3 centimeters. The depth of lemonade, h, is a function of time t in seconds. The volume of lemonade in the can will change at a rate given by minus pi divided by 2 multiplied by the square root of h. As the person quenches their thirst, the depth of lemonade goes down and down until the can is empty, at which point the depth of lemonade in the can h is equal to 0. At time equals 0, so when the can is full, the depth of lemonade is 9 centimeters. So firstly, we need to formulate the differential equation which models the rate of change between depth of lemonade and time, so dh by dt. Then we want to find the particular solution to the differential equation given the initial value of depth h equals 9 at time 0. This will give us a function h of t which will allow us to predict the depth of lemonade at a given point in time. We know that the rate of change of volume with respect to time, so dv by dt, is equal to minus pi divided by 2 multiplied by the square root of h. We also know that the volume of a cylindrical can is equal to pi r squared h. So at time t equals 0, the volume of lemonade in the can is equal to 3 squared multiplied by pi multiplied by h. So that equals 9 times pi times h. Using the equation volume V equals 9 times pi times h, we can find the rate of change of volume of lemonade with respect to time by taking the derivative with respect to time of both sides of this equation. On the left-hand side of the equation, to find the derivative of v with respect to time, we need to use the chain rule. So the derivative of v is 1, and then that's multiplied by dv by dt. Similarly, on the right-hand side of the equation, we want to find the derivative with respect to t of 9 pi h. So in this case, 9 pi is a constant. So again, we need to use the chain rule. So the derivative of h is 1 multiplied by dh by dt. That leaves 9 pi times dh by dt. Now we know from above that dv by dt is equal to minus pi divided by 2 multiplied by the square root of h. So we can substitute for dv by dt in our equation. This leaves minus pi divided by 2 multiplied by the square root of h is equal to 9 times pi times dh by dt. We can then divide both sides of the equation by pi to eliminate it, and then separate the variables such that all variables involving h are on the left-hand side and all those involving t are on the right-hand side. So we're left with h to the power of minus a half, which is the same as 1 over the square root of h, multiplied by dh is equal to minus 1 divided by 18 multiplied by dt. We can now find the general solution of this differential equation by integrating both sides of the equation. So we have the integral of h to the power of minus a half dh is equal to the integral of minus 1 over 18 times dt. On the left-hand side of the equation, the antiderivative of h to the power of minus half dh is 2 times the square root of h plus a constant of integration, which we'll call c1. And on the right-hand side of the equation, the antiderivative of minus 1/18 times dt is minus 1/18 multiplied by t plus a constant of integration, let's call that c2. Dividing both sides of the equation by 2 and allowing c to equal c2 minus c1, we're left with the square root of h is equal to minus 1 over 36 times t plus a constant c. This gives us our general solution. To find our particular solution, we need to solve the equation and find a value for c using our initial condition where the depth of lemonade is 9 centimeters at time t equals 0. Substituting these values into our equation, we have the square root of 9 is equal to minus 1 over 36 times 0 plus c. And replacing c in our original equation, we get the square root of h is equal to minus 1 over 36 times t plus 3. And squaring both sides of the equation, we get our particular solution where h is equal to 3 minus 1 divided by 36 times t all squared.